10 past 8 p.m. GMT. So I welcome you, Frank, to this VSA Online webinar. So today we are sending it in Teams because of problems with Zoom. So the webinar the recording will be available if I will figure out how to extract the video by the end of the webinar from Teams. But nevertheless, so I should stop talking and leave the floor to you. So please.
Thank you so much. Hey everybody, I'm Frank. Just a brief intro about me. I'm a PhD student in statistics at UC Berkeley. I kind of was introduced to VSA and the techniques concepts around it because I've been hanging out in the Redwood Center. One of my co-advisors is Bruno Olshausen, which some of you might know. And today I'm going to be going over a graph embedding method using tensor products and orthonormal codes, giving some of its nice properties, some of the neat things you can do, as well as comparing it to existing techniques. As a newcomer, I am, you know, I I'm aware that I don't know the entire field of VSA, so if some of this seems rehashed or old news to you, please forgive me. But hopefully, we can all. Here's a brief outline of the talk. It's going to be divided in two. The first part is going to go over the main graph embedding methods, and the second part is going to give a brief look at alternative bind and sum schemes that are similar to the proposed method. Okay. So before we get into it, why graphs? Why are we interested in embedding these things, and why do we even need to embed them in the first place? Well, first of all, among many other reasons, graphs are a natural way to express relational data. You know how entity A relates to entity B, and they pop up everywhere: social networks, recommender systems, knowledge graphs. Tracking disease. So in a variety of applications, they're at the forefront. However, they are discrete objects, so a lot of concepts that exist for continuous things might not translate so much to graphs. Like, say I wanted to optimize over a space of graphs. Continuous space, take gradient descent with respect to some objective. Discrete space, maybe you're doing a combinatorial search. Maybe you try to embed these as continuous things and do some kind of continuous relaxation. I don't know. Same thing with storage. How do you efficiently store these discrete things? Continuous objects, maybe you can take a low dimensional projection. And riffing on this idea of the discrete versus continuous, there are a lot of powerful techniques that have been developed for continuous value data that don't seem to play well with discrete objects. So what's the fix? Well, maybe let's take these discrete things, these graphs, and try to embed them in a continuous space in some structure preserving manner. And how we're going to do it, at least for the method proposed here, is we're going to try to specifically embed the relational data, the edge set. So here's a bit of a background. The proposed method is a bind and sum approach. What that means is by representing the edge set, I'm going to represent this big set, as a superposition or a sum of the edge embeddings. And to generate these edge embeddings, I'm going to use a binding operation to bind together vertex embeddings. So here are two recent examples that specifically take this bind and sum approach for knowledge graphs. So again, this bind and sum approach is not new, commonly known. And the binding operation I'm going to use, the tensor product, was first proposed by Paul Smolinski in the general context of role filler binding in 1990. And at least from my understanding, originally the field of VSA kind of moved away from the tensor product because the dimension of it explodes with both the binding order, how many things I'm binding together, as well as the dimension of the original space. Like if I'm binding two things together, then the tensor product, the second order tensor, will scale quadratically. Later in the talk, I'll try to circle back on this and maybe try to convince you that these problems with the tensor product, especially compared to these dimension preserving binding operations, are a non-issue, at least for graphs, and the tensor product is competitive with these alternative binding operations. Code I'm going to use can also be characterized as just falling under this general umbrella of unit length codes, which also include binary and phasor codes, which seem to pop up a lot in VSA literature. So let's kind of do some preliminaries. So again, I want to embed a directed graph, which is just a tuple consisting of both a vertex set as well as an edge set. And again, we want to embed this edge set. If we really wanted to, we could also embed the vertex set by assigning each vertex to its self loop. Introduces some confusion, but can be done. And we assume that every graph that we're going to embed, its vertices are part of a larger vertex set. So in essence, what is being proposed here is an embedding technique for a family of graphs whose vertices all lie within some big set V. And here's how we're going to embed the graph in 3 simple steps. First, we're going to assign a vertex code to each vertex. Then, for each edge in our graph, we're just going to generate its edge embedding by taking the tensor product, fixing a basis. This is just the outer product of the 2 vectors. And then to represent the edge set, we're just going to sum all of the edge embeddings together. So a kind of very simple, naive approach, but as we'll see, it both offers a lot. You can do a lot of natural graph operations with these embeddings with the right choice of code, and it has some nice theoretical properties. And here we're going to kind of look at specifically first the binding operation, the tensor product, and how it relates to superposition. So again, superposition principle basically says that to represent a set, to embed a set, we're going to embed it as the sum of its singletons. And so now let's specifically consider embedding a edge set. So in this first equation here, we're considering a graph where we have a bunch of different source vertices that all point to the same target vertice. And so we can see that it is quote unquote linear in the first argument in this case. In the second equation, we're considering a common source vertex with a bunch of edges pointing to different target vertices. And you can see that by the superposition principle, it implies that it must be linear in the second argument. So these 2 equations together means that any edge embedding that respects superposition induces a bilinear map from the vertex embedding space via this map. So now, as long as we're talking about bilinearity, there's something called the tensor product has a certain property called universality, where basically every such bilinear map psi tilde can be uniquely linearly derived from the tensor product, has a corresponding unique linear map psi star that makes this diagram commute. So in this sense, the tensor product maps into every edge embedding space for every edge embedding method that respects superposition. And it is, in this sense, the most general edge embedding method. And examples of this include the Hadamard product, which is just the diagonal of the tensor product, circular correlation sums along one diagonal, and the convolution sums along the other diagonal going in the opposite direction. So just a quick recap of what I covered here, since I might have went a bit fast. Assuming our edge embedding respects superposition, you get these 2 equations, which mean that the edge embedding must be bilinear. As long as I have a bilinear map, any such map must be uniquely and linearly derived from the tensor product. So the tensor product is the mathematically canonical binding method for all edge embedding methods that respect superposition. And it can do anything that these other binding methods can do. So that's a nice thing about the tensor product. But now let's go on to the other side of the coin, the vertex code choice. So up to this point, we just assume we're using some vertex embedding, and we're going to, embed the graph using the tensor product of the vertex embeddings. So now the question arises, what are good vertex embeddings? And specifically, what is a good choice of vertex code that allows these graph embeddings to be as expressive as possible? Turns out that the natural answer is orthonormal embeddings because they allow for accurate graph operations. And here are some of the graph operations that you can do. So at this point, we're going to assume that all of the vertex embeddings, I'm abusing notation, and so V represents both the vertex and its vertex code. We're going to assume that all vertex embeddings are orthonormal. Then, using the tensor product and these orthonormal codes, here are some natural graph operations that you can do. You can do edge deletion by adding or edge deletion or addition by adding or subtracting the appropriate edge embedding. You can do vertex edge queries, ask if a vertex or an edge exists in this graph. And again, this is all leveraging orthonormality. I can do edge composition or compute k-length paths by taking the kth power of the kth matrix power of this graph, of the graph embedding. I can extract subgraphs, by conjugation with the appropriate projection matrix, where S is just the matrix whose columns are the vertex codes of the subset S. Transposition, alternization, and symmetrization all have natural analogs. Transposition, I flip the direction of all arrows in my graph. Symmetrization, I'm working with undirected graphs. Alternization, I'm putting a sign on my edges. So now, positive or negative sign will reverse the direction. With respect to these graph embeddings, there's a natural metric via the trace, where the trace actually counts the number of edges in the graph. And in this sense, via this relation right here, the Frobenius norm is the natural graph metric, which counts the number of different edges between these two graphs. The gram matrices also have a special meaning here, where they represent a symmetric, or where they represent a quadratic form that computes the in and out degrees. So for example, if I wanted to compute the in degree of a specific matrix, I can multiply it on the left and the right by the appropriate vertex embedding V, and that would give me the in degree of V, and similarly for the out degree. You can do graph homomorphisms naturally with these graph embeddings, where again, to translate a graph using embeddings, using a codebook 1 to the same embedding, but using a different vertex codebook, I can just do conjugation by an appropriate projection matrix. And similarly, I can extend this to computing something called the graph homomorphism coefficient, which kind of computes how good a vertex function is to inducing a graph homomorphism. So I've gone over all of these operations quite fast, but hopefully this subset of the possible operations is enough to convince you that the generated graph embeddings are rich, and many natural graph operations correspond to simple linear algebraic operations. However, there's one problem. We did assume that the vertex codes were orthonormal, so many of these graph operations all hinged on the vertex codes being orthonormal, so things could cancel out. However, this is inefficient, since we can pack at most d orthonormal vectors in a d-dimensional space. So what's the fix? Instead, we appeal to approximate orthonormality, which actually allows us to pack exponentially more vertices into the same space. At this point, before I get into the more mathy section, does anyone have any questions so far?
No. One participant had the microphone unmuted, so it was some echo.
Oh, okay. Yeah, no problem. Okay. So now let's get into approximate orthonormality in high spaces. So first, we say a set of vectors is epsilon orthogonal if their dot product is absolutely bounded by epsilon. So, take their dot product, and if it's at most epsilon, or nearly orthonormal. So there's a theorem called the Johnson-Lindenstrauss theorem, which basically states that we can pack at most exponentially many epsilon orthogonal unit vectors in a d-dimensional space. And so this is exponential scaling in D rather than linear if we're assuming perfect orthonormality. And in fact, via a specific code called spherical codes, we can match this packing limit. So what are spherical codes? Quite simply, they're just vectors drawn uniformly from the unit sphere. I'm going to skip all the proofs, but you can show that their dot product or a version of their dot product follows a beta distribution with mean 0 and variance 1 over d. And you can also show that assuming a fixed error threshold of violating epsilon orthonormality, you can pack this number of vectors into the same space using these spherical codes. So spherical codes achieve the Johnson-Lindenstrauss upper bounds. And they maximally pack this space. And they're flexible. They're easy to generate. Since I'm drawing them IID from the unit sphere, there's no dependencies between the codes. So if I need to delete one or change another, I don't need to change the code book. So again, to recap, spherical codes, you can characterize the behavior exactly. They optimally pack a d-dimensional space, and they're nice to work with. And so here's a recap so far. First, I went over the graph embedding method as well as some operations you can do. Looking at the binding operation, we saw that tensor product is actually the canonical, most general binding operation, where assuming your edge binding method obeys superposition, you must have a bilinear map, and any such bilinear map must filter uniquely through the tensor product. For our choice of vertex code, we see that spherical codes maximally pack the vertex space and achieve the Johnson-Lindenstrauss upper bound. And our graph embedding method is very expressive. It can naturally represent many graph operations as linear operations. So that's and we'll conclude the first section with kind of a connection to adjacency matrices. So it turns out, or you might have noticed it before when I was going over some of the graph operations, that a lot of them seem to be very similar or exactly similar to things you could do with adjacency matrices. It turns out that in the exact orthonormal case, adjacency matrices are a special case of the method proposed. Specifically, let's say that we embedded our vertices as coordinate vectors. Then the adjacency matrix is precisely just the sum of the tensor products of these edge embeddings. And in fact, again, assuming exact orthonormal vertex codes, every graph embedding is an orthogonal change of basis away from some adjacency matrices. And this immediately tells us that our graph embeddings can do anything that adjacency matrices can do, including graph Laplacians. The spectrum is preserved under these change of bases. I'm not going to get into it, but a lot of cool things you can do with our graph embedding method. And how our method changes things up is the use of spherical codes and approximate orthonormality to drastically compress these adjacency matrices. So you can show that assuming epsilon orthonormality with m vertices and n edges in the graph, our graph embeddings are pretty close to a adjacency matrix with respect to the Frobenius norm. And specifically, again, the draw of our method is that it offers a drastic compression of the adjacency matrix. Usually, to store an adjacency matrix, assuming I have n vertices, the adjacency matrix will be n squared, right? So it scales with the number of vertices and not the number of edges, which seems kind of wrong. Because I'm not really concerned with looking at all of the pairwise interactions. I'm just concerned with storing all of the relevant ones that exist in my graph. Under the proposed method, you can show that actually the number of parameters now scales with k, the number of edges, rather than n, the number of vertices. So in this sense, using approximate orthonormality, you get a much more favorable scaling that scales with the quote unquote right quantity, the number of edges rather than the number of vertices. And this is probably especially useful for large sparse graphs, which allow you to drastically compress the adjacency matrices of such graphs. Yeah, so that concludes the first portion of the talk, which is kind of going over the graph embedding method, as well as its related properties. Are there any questions up to this point? Okay. In the second part, I guess I'll be going over a brief comparison to existing um, existing or yeah existing popular methods, and hopefully specifically I'll try to challenge some conceptions you might have about the tensor product, about how it's inefficient, yada yada, and how if you peel back the picture, if you look a bit closer, at least in the context of graphs, these are concerns about the inefficiency of the tensor product actually turn out to not be so important or turn out to be non-issues. So first, what is the problem with the tensor product? It just uses too many parameters. It scales poorly with both the size of the original binding space as well as the binding order. Well, for graphs, the binding order is always small. Usually it's either 2 or 3, depending on if you want to tensor on a type to the edge. It also scales superlinearly with respect to the original binding space. If in the case of the proposed method here, it scales quadratically. But perhaps this quadratic scaling or the superlinear scaling is necessary. And how does compression affect capacity? So for this section, I'll be specifically considering two quantities: the memory of an embedding method, that is the number of parameters uh, that the embedding method takes, as well as the capacity. So that is how many objects can I store in superposition using using a method. We'll see that, in fact, compressing the tensor product might have adverse effects on the capacity, specifically how many things can I store in superposition. And we'll see that some dimension preserving bindings, including the Hadamard product, have the same memory capacity ratio as the tensor product. That when I compress the tensor product, I have a proportional penalty on the capacity, on the number of things I can store in superposition. So really, the memory capacity ratio of both methods is the same. So specifically for this comparison, we'll be looking at the vertex query. Given a graph embedding, we want to see if it contains a specific vertex. I'm going to skip over the proofs and all the math, but the end result is, assuming that the vertex code is d-dimensional, we cannot store more than d squared edges in superposition without significantly compromising accuracy. And this behavior, we arrive by both bounding the probability of error, that is incorrectly retrieving the wrong vertex, as well as the norm of the noise term relative to the signal term. So the punchline is, for the tensor product with spherical codes, we need d squared parameters to store d squared edges. So we have a memory capacity ratio of 1, right? Our memory is d squared, our capacity is d squared. And so what causes this behavior? It's because orthonormality causes destructive interference. So let's say I try to unbind this edge by A. If they match, then this becomes 1, and what's left is B, the vertex I want. However, if A and C don't match, then their dot product is going to be small, which shrinks this term close to 0. So this is kind of an intuition on why orthonormality is a key ingredient and why it helps the memory capacity ratio. Now let's look at a popular alternative binding scheme, the Hadamard product with Rademacher codes. So Rademacher codes are just random binary codes. Hadamard product, just entry-wise multiplication of two vectors. So this is a dimension-preserving operation, and it seems to be quite popular from the VSA papers I've read through. If we look at its performance on the same exact vertex query, we'll see that assuming the vertex code is d-dimensional, we cannot store more than d edges in superposition without significantly compromising accuracy. So again, our memory is d and our capacity is d, and we have the same ratio of 1 compared to the tensor product and spherical code. So in actuality, if you actually consider like not only the savings in dimension, but also the penalty in capacity, the Hadamard product with Rademacher codes performs the exact same as the tensor product and spherical scheme. And so what's the intuition? The unbinding operation for the Hadamard product doesn't have destructive interference. It does not destroy unlike pairs. So on the right, if I unbind by A on the left, this term still is going to be just a Rademacher vector. And so this noise term is still going to just be another Rademacher vector. It doesn't shrink in any way, unlike in the orthonormal tensor product case. And you can extend this to arbitrary n-order graph operations. So the vertex query was the first order graph operation, edge composition is a second order operation. For both schemes, they actually have the same scaling in the memory capacity ratio of this scaling. And so this analysis kind of keys in on a fundamental trade-off where savings in memory can be offset by a proportional penalty in capacity. So when you look at these alternative binding methods that preserve the dimension, you also have to consider how does this adversely impact the number of things I can store in superposition. And in this case, in the Rademacher case, you can see that it's a proportional offset. And so you're not really gaining anything at the end of the day. And you can extend this analysis to other alternative binding operations. So for example, convolution, we know in the Fourier basis is just the Hadamard product. Circular correlation in the Fourier basis is essentially a permute and then Hadamard product. So up to a Hermitian change of basis, these are all equivalent to the Hadamard product with possibly a permutation. So you can kind of assume all of these other popular binding operations under the Hadamard product. So now let's look at the Hadamard product and its expressivity. So we saw previously that, okay, maybe you're not gaining that much. You're not gaining that much when you're saving in memory because there's a proportionate penalty in capacity. What about the expressivity? When you compress the tensor product, what else are you losing? Well, in this case, specifically for the Hadamard product with permutations possibly applied, you are losing some expressivity. So for example, the Hadamard product is symmetric. So naturally, it can't represent directed edges, right? Because it's symmetric. However, to induce directedness, we can permute one argument. However, if we do permute one argument, now this makes edge composition impossible without knowing beforehand A. Like if we unbind by A, then we need an oracle operation where we kind of know like, oh, A is in this edge, so maybe I permute A on this left-hand side. So in this case, there's kind of a fundamental tension for the Hadamard product between directedness and edge composition. So now we can extend this to alternative to any other binding operation and encoding scheme. The tensor product we saw is the most general. Anything these other schemes can do, the tensor product can do. But when you compress the tensor product, what are you losing? In this case, we see that we're losing. There's it's a either or choice between directedness and edge composition. For other operations, what else are we losing? And since in the specific case of Rademacher codes, it has the same memory capacity ratio, why not just use the tensor product from the get-go? So here's a recap of what happened in this section. We specifically looked at the tensor product and its memory capacity ratio compared to the Hadamard-Rademacher case. We actually saw that, one, it has the same memory capacity ratio as this supposed dimension preserving method. It also has more expressivity than this dimension preserving method. And the same concern can be extended to other similar binding operations like the convolution and the circular correlation. And specifically for graphs, maybe these concerns about scaling don't apply because compression might have an adverse effect on capacity. In the first part, we also introduced our graph embedding method, showing that the tensor product is the most general canonical binding operation. We showed that the choice of vertex code, the spherical code, achieved maximal packing, and our method is both easy to generate, easy to work with, flexible, expressive, and also has a nice generalization to adjacency matrices. So that's kind of a recap of everything I've covered up to this point. I'm sorry if I went a bit fast, but I wanted to kind of cover everything. Are there any questions up to this point? Or actually, maybe let me just go over the conclusion, then I'll field questions if anyone does have them. So in conclusion, what happened here? We introduced a new embedding method that has both nice theoretical properties, nice theoretical characterization, as well as achieving some optimality, some optimal packing stuff, as well as good expressive power. We showed specifically that the binding operation we used is intimately connected to superposition. We also showed that perhaps preserving the dimension via the Hadamard product or convolution or related binding operations isn't as good as previously thought because there's a fundamental trade-off between memory and capacity. And along this vein, maybe when considering these binding operations, there should also be a consideration toward flexibility, expressiveness, and ease of transfer. We saw that for the Hadamard code, compressing the tensor product to the Hadamard code had some adverse effects on being able to represent directed edges versus edge composition. So just 4 key takeaways from this talk. And I'd like to thank Dennis, Bruno, Giles, and the entire Redwood Center for all of their help, for the thoughtful, helpful discussions I had, and the many pointers they gave me. And I'd like to thank everybody here for listening to me and sitting through my talk. And yeah, thank you, everybody. And I'd be happy to answer any questions.
Thank you, Frank. Thank you very much indeed for your talk. Extremely interesting. If you would ask me. So, any questions from the audience? Paul, please. Paul, can you unmute yourself?
Yes, it always takes a long time to find the
yeah.
button.
Yeah. Hi. Good to see
Sorry.
you.
Good to be here. Thank you, Frank. Very, very interesting work. This is Paul Smolinski.
Oh, hey, Paul.
Hi. Really appreciate this work. It's nice to know that there's one other person in the universe who thinks that tensor products have been grossly maligned for their size. So, but I wanted to ask about something very early in your talk. I didn't want to interrupt the flow, but very early in the talk, you made a connection that I didn't get, which is how superposition entails bilinearity. Could you state that the theorem again? What is that implication actually?
Yeah, I can go a bit slower. So, superposition, I think by that I mean we want to represent a set as a sum of its constituents. So, if we're considering a case where we have an edge set with a bunch of different sources pointing into the same target, then naturally this requires, if you think of union as addition, naturally this requires that the edge embedding be linear in the first argument. If we take the case where we have a single source pointing into multiple targets, then this requires that our edge embedding method be linear in the second argument. And formally, this does induce a bilinear map from the vertex embedding space, where for this, where I send these two vertex, where I send this tuple specifically to the resulting edge embedding. And you can show that at least this induces a bilinear map, maybe not from RD, but from the subspace spanned by the vertex code. So assuming it respects superposition, then it does induce a bilinear map.
I understand. I understand that. I understand
Okay.
that one can define a bilinear map. But I heard something stronger that
Yes.
something has to be bilinear
Yes.
rather than something can be bilinear, and I didn't understand what the something was and under what conditions it follows that it has to be bilinear.
I think as long as it respects the superposition principle, uh, so if it respects the superposition principle, you agree that it has to follow these two equations, right?
That's the definition, I would say. Yeah.
Uh-huh. So if it follows these two definitions, then
Hmm.
there's a natural induced bilinear map from the vertex, this Cartesian product into the edge embedding space called psi star, which is defined like this, psi star, like so. Or psi tilde, my bad, psi tilde.
Okay, so um, okay, so this is a different result than what I was trying to understand. It's not about the universality of the tensor product. It's about the universality of bilinearity in some function that I'm not super clear on. So I understand that when we're trying to embed edges, then that's a binary entity in edge. And so it's natural to look for bilinear operations to embed it. And I understand how the superposition principle plays into that. And so maybe I understood what you actually claimed all along. I just didn't, I imagined that there was something stronger being claimed than what was actually being claimed.
Yeah. All I'm claiming is superposition entails these equations. These equations entail that the edge embedding induces a bilinear map, like so, this psi tilde. As long as we have a bilinear map, by universality, there must be a corresponding map from the tensor product. So any edge embedding that respects superposition must and can be linearly derived from the tensor product.
Okay. Okay. Thanks.
Yeah. Any other questions? I'm sorry if I went a little bit fast. Yeah.
Frank? Oh, that's a question.
Go ahead.
Do you wanna
I'll ask
say
my
something?
question
Okay.
later.
Oh yeah. I was just curious, it's like, I think you presented very convincing case that like one would like to use binding to do the presentation on graphs. And at the same time, it's right now, of course, there's like, a lot of excitement is going on about this graph neural networks that just this kind of learnable models that kind of producing this kind of trainable embeddings. Like, oh, I don't think anyone has like a good clue what eventually this embeddings are doing, but they seem to provide good results. But from what I've seen in the literature, there is no like binding operation is not used in any way in these models. Do you do you have to comment anything on that? Like, are they missing something fundamental? Could they be improved fundamentally if the binding is somehow introduced in such kind of models?
Yeah. I don't think I can speak too deeply on the topic since I know very little on it. From what I understand, how graph convolutional networks really work is like you have some kernel that you shift over all of these local neighborhoods of the graph. And so like kind of you assume it's like a little bit agnostic. Well, maybe not agnostic, but it's like you're really just taking a lot of local information and kind of taking a weighted sum of the local information. And I think you're assuming that the local neighborhood is fixed, because I'm not sure like if the local neighborhood had a lot more edges than your kernel, like how would that jive? But it seems to be like, okay, I already have a graph structure and I want to kind of take this filter over this graph structure and use it in my computation. Whereas here the approach is more like I have a family of graph structures that I want to embed in a vector space. So I think this approach might be a bit more in line with, let's first port graphs into vectors and then let's feed it into any general algorithm that processes these vectors, including just just a usual neural network, not necessarily of the graph convolutional kind. So that's my understanding. Like maybe there's a maybe there's a slightly different approach that graph neural networks take, where they assume a graph, that they take convolution and specifically adapt it to a graph structure. Yeah.
Thanks for the comment, Frank.
So I suggest, Paul, you go on with your question, and then we transfer the voice to Ross.
Okay. I have two comments. One is in relation to graph neural networks that was just brought up by Dennis, that you were, I think, talking about convolutions over graphs, graph convolutions. There are graph neural networks where the links are used basically to pass information between the nodes. And so a node collects information from its its inset and combines the information it receives from these nodes in some fashion, which allows it to then propagate that information to its outset. And so it would be interesting to look at how your embedding of the graph supports that kind of operation of propagation of vectors around the graph. I assume it would be a very straightforward linear operation to apply to your embeddings to do one of the iterations that you see in a graph neural network, in which information is sent over the links and combined at the nodes, at least when the composition is addition anyway.
if I'm understanding you correctly, like I think kind of a natural step would be, let's say like I have a codebook V for the domain and a codebook W for the codomain or the or the target space. So from domain to the target space. Then I would want to learn a graph whose edges are V or whose edges are WV transpose, something like that. And then for a certain value, for a certain superposition of things in V, I just, take a matrix multiply using my graph embedding, something like that.
Mhm.
If I, yeah, yeah.
I think
I think, yeah,
something like that. I'm not entirely following, but
yeah.
that's the general intuition I was having too.
Mhm. Yeah.
Okay, and the second thing I just wanted to point out in the chat, I'll put a link to a paper that was done by Coleman Haley and myself in the computational linguistics meeting in 2020, which uses spherical codes in tensor product representations for trees, not graphs,
Mhm.
and showed the way how the scaling, the capacity does scale as the number of nodes in the tree that are occupied by a symbol rather than the number of nodes in all, rather than the number of all possible nodes in a tree
Mm.
of a certain depth. So that's a similar kind of result that you were claiming about scaling not with the square of the number of vertices, but with the number of edges. It's about trees and it's about linguistic trees specifically. But I think that you might find that some of the results that you're talking about in the context of graphs have counterparts in what we were doing with trees.
Yeah, yeah. I'll take a look at the paper and how the techniques they used. Yeah, interesting.
Okay.
Well, I mean that's good to hear because I was like, I mean this seems kind of like I was wondering why no one had looked at it before. It's like it seems kind of like the first thing one would try, And so
Yeah,
yeah,
there may very well be other work that's tried it as well, but
yeah.
I can only tell you what I know about. So, all right, thanks. Very interesting.
Thank you. Yeah.
And so the paper you have on arXiv is reports basically the results you talked about today. Is that right?
Yeah, so one of them is a paper introducing the method that probably covers up to the first part of the talk. There's another
Mm-hmm.
companion piece. I can post the link
Mm-hmm.
that is a bit more statistical and goes over the comparisons to the Hadamard-Rademacher case. Gives a derivation of the tensor product from a naturality and a universality argument. So yeah, second part comes from second paper, first part comes from first paper, and I can post it, the arXiv link.
Okay, great. Yeah, I see
chat.
them both on the
I
arXiv.
I would suggest also to I will put these links. I will link this material from the website so that people can find it easily. If you can send me them.
Okay. Yeah.
So Paul, are you done with your comments? So,
Yes, I'm done.
Yeah. Okay. Thank you. So then, Ross, please.
Yeah, thanks very much for that very interesting presentation, Frank. I'd like you to clarify something for me and then potentially lead into a comment from that. I think it was around about slide 24, 25, you were talking about comparison between tensor product binding and, yep, that's the one, and the preceding slide, I think. Yeah, so you're right. So that bit down the bottom there, what you're basically saying is that because you've got orthonormality, you are effectively destroying unwanted terms in the result.
Exactly.
Yeah, and so and then the following slide, you're then saying, yeah, but if we do a Hadamard product, they just hang around as weird noise terms. I think then this is the comment is that I think also there's an intermediate option. So if you've got a tensor product, you can decompose that matrix of those cross terms into a concatenation of d many Hadamard products of permuted versions of the argument vectors that you're combining with the tensor product. And in the past, what I've done is I've basically used a very small subset of those. So rather than just using one Hadamard product, used a small number like 5 or 15 or whatever of of Hadamard products of different permutations of the arguments. So this is some work I did with Simon Levy a long time ago on trying to find isomorphisms between graphs. And then the net result of that is that instead of your noise terms being reduced to 0, you just reduce their amplitude. It means that if you, it probably then commits you to using something like a recurrent calculation. So you repeatedly think of it as a filter. You're repeatedly reducing the amplitude of terms you don't want. But it's and it's, I guess this also speaks to Paul's comment way back when he was talking about tensor products being maligned. I think this is sort of an because of the space occupying things. So this is basically an engineering hack to say can we get some of the properties, but while for other reasons reducing the size of the number of things we need to keep track of. But it's just worth thinking about, I think, rather than sort of this stark opposition between you've got this complete property at one end and complete property at the other end. But if we can engineer things in the middle, there might be good engineering reasons to try to do that.
Could you so you said you could decompose this tensor product into a bunch of Hadamard is there like a tensor product operation interspersed in there?
Well, all I'm saying is if you think of the circular convolution, effectively what you're doing is you're dividing up the outer product into a series of diagonals and you're summing across the diagonals. But another way of thinking about that is if you think about the diagonals running in the opposite direction, effectively what you're doing is you're creating a bunch of Hadamard products and just summing them together. So you can view the circular convolution as being the sum of d many Hadamard products of different permutations of the arguments.
I see.
So basically, what I ended up doing was saying, well, if you think of just with Rademacher representation, think of each one as being a bit. You've got 0 error correcting capacity in that. So essentially, if you've got a binding, a Rademacher vector representing a binding, if there is 1 bit in error in the queue that you're querying that with, then there will be 1 bit in error in the result. So it's got 0 error correcting capacity. So basically, the intuition in what I was doing in this other stuff was to say, well, if I have multiple versions of this binding and unbinding operation going on, but I use different permutations, then if you like, but then I take the results from all of those and add them together, bundle them, superpose them. If we've got 1 bit in error on the queue, its location relative to the bits in the other argument will vary depending on the different permutations that are used. So you end up then saying, well, basically it's like I'm taking a bunch of noisy results and I'm averaging them together to get a result which is closer to the intended result.
Yeah, I see.
Yeah. So
that
it's
makes
sort
sense,
of an error correcting version of, and basically it's what it's relying on is instead of just having one tiny fraction, one deth of all the elements from the cross product of the tensor product, you're taking a few multiples of that and saying, well, from those I can get a less noisy result. And so, just putting that back into the kind of terminology you're using in those slides there, it's what you're doing is effectively reducing the scalar multiplier of those noise terms. Instead of being 1, it's something less than 1. It's certainly not 0, but it's a step in the right direction. And so if you had something like a recurrent circuit where you're sort of pushing that those values repeatedly through that filter, then you can drive those values down lower.
Was there any analysis on like how this affects the number of things you can store, or like
No. I mean, my
okay.
mathematical ability is absolute rubbish. Couldn't prove a thing to save myself. So it's waiting for somebody to actually look at it properly. There is, interestingly, one of the other people who's spoken in the seminar series, Alex Kelly, has done some work.
Alex Kelly.
Picked up that. So that was just a sort of a side issue in this thing about mapping, finding isomorphisms between graphs. But Alex Kelly picked that up and showed that was strongly related to a number of historical models of memory in mathematical psychology. And those include things like convolution models and tensor models and so on. So, I mean, once again, it's not it's not math in the sense that you've been doing it here, but at least sort of it's got interesting cross links across to models that people thought were actually decent mathematical psychology models of memory. So it's sort of closer in spirit, perhaps, to what you'd want to do.
Definitely, I think, especially for me, one of the really nice things I like about this graph embedding method is that doing graph isomorphisms is so natural. It's just just a change of basis is all it really is. So
although what Simon Levy and I did was not a change of, well, it probably was in essence, but it was it actually took a quite different approach. A guy called Marcello Palillo was using dynamical systems to find maximal cliques in graphs, and then using that to find isomorphisms. So if you find the maximal clique in a specific graph, which is sort of the outer product of two graphs, corresponds to the isomorphism between the two graphs. So I guess I'll forward that link. I'll forward the link to the paper that I did with Simon Levy to Evgeny later, and he can put it up in the VSA mailing list. But that then has links across to this Palillo work, and that's based on this evolutionary game theory stuff, which then there are other links elsewhere saying, well, actually, what this corresponds to is Bayesian inference. So, there's a whole bunch of interesting, whole bunch of interesting cross links to other topics.
Excellent. Yeah, if you could post that the papers, so some of the related papers in the chat, I'd be happy to look at them.
Yep.
Yeah.
Okay, I've monopolized enough time. Thank you very much for the talk.
Thank you.
Okay, so we have another hand up from Dennis.
Yeah, that is just a very brief note, because sort of reflecting on what Ross has mentioned. There was a relatively recent preprint by Naoki Hiratani and Chaim Sempolinsky, and essentially in that preprint, what they've done, they've generalized. I mean, the tensor product there is the main actor essentially, right? Because that's the starting point, as Frank was saying, for sort of other binding schemes. And there they sort of generalize it, like, and it, like, they propose a scheme that goes beyond the circular convolution. So it's kind of parameterizable scheme. And in the sense, I don't think that it will be better in terms of capacity analysis, but it's sort of, it's what I think it's beautiful about the schema that now it's not a continuous anymore. You say, well, there is a tensor product, or you have to go like, circular convolution or Hadamard product that reduces to n. So you can essentially choose pretty much, as far as I understand, any number between n and n squared, and that will be the result of your binding. And so that, which kind of now makes just a continuum in between them. But that was just kind of side note, not really related to the graphs, but I think it's sort of related to what we touched on today on this sort of different binding operations.
Right, right. Oh, interesting. Yeah.
Yeah, it's
I'm
just like 3 months old, though. It's very recent preprint.
I'm assuming that any such method, assuming it obeys superposition, is uniquely characterized by some big, like what do I send the basis tensors to? BI, tensor
Yeah,
BJ.
yeah. I think they actually make essentially ternary. This is parameterized as a three-dimensional tensor, as far as I recall. Yeah. So because
okay.
it's
Yes.
effectively states, what sort of what components of your outer product are going to contribute to what new dimension after the binding. So that's kind of a very explicit way to parameterize it.
Yeah, it seems like, no, I've never, I guess like throughout this paper I've just considered tensor product, but no, I think it's definitely very interesting where like, there's a continuum between n and n squared where you kind of just successively compress the tensor product. Yeah, interesting.
Yeah. To me, it was very interesting message. I never thought about it, and I was like, okay, yeah, wow, that's pretty neat. Like very generic way, to think about it, and the way also to introduce this, continuum. So it's essentially it's not like, discrete choice, like what exactly do you do? So it's.
Wow. Interesting. Yeah.
And I send the link to the preprint in the
I see.
chat.
Yeah, I was going to ask. Yeah.
Yeah, it's in the chat already.
All right. Thank you.
I'm just trying to see the chart. Yeah, I see your. See quite some. I just don't want them to disappear. These links. So somehow it would be nice to collect these links in one email.
Yeah, Evgeny, the easiest might be if people email the links to you, and you can then create one composite email back out to the group.
Yeah, may I ask
I can do it,
all
Evgeny.
of you who yes.
I think I should be able to collect the links, Evgeny. So we'll send it to you, and then you can spread it as a sort of to the whole mailing list.
Yeah, because I think this discussion is extremely interesting is interesting, but is of very high importance. I mean, with respect to application, this graph isomorphism, but also, from general understanding of VSA capabilities. And I mean, the people working with VSA, they're not many are not mathematicians or lack certain mathematical background, and talks like yours, so they shade some light on what is going on there. So
I don't think I'm not a mathematician either, but I guess
I guess
I know enough. I know enough. Yeah.
Okay. Don't be shy.
Can I jump in with one short observation?
Sure.
Mm-hmm. Yeah. Which is, Frank, I mean, the presentation as you've given it, you've treated the vertices as elements from a dictionary, and so the connotation, although it's not exactly what you said, is that effectively you're treating these as the vertices as atomic elements. They're just things that we're finding the edges between. We're not talking about their internal structure. But one of the neat things about VSA, the tensor product, this whole area of concern is that we can represent complex composite structures as vectors, and so it's possibly, I mean, if you really want to give yourself a headache, thinking about the possibility of the vectors actually being representations of, sorry, the representations of the vertices actually being representations of complex composite structures in their own right. So each of the vertices might be a graph in its own right. Now, obviously, I mean, that has implications for the dimensionalities of the the vectors that you're using to represent the vertices. If you're thinking about representing complex things, then obviously you need a longer vector than if they're just some relatively short dictionary of atomic items. But the other thing, obviously, is you also have to worry about the similarity between the vertices, because they're no longer approximately orthonormal. Although if you were to say, I actually, if the graphs that are the vertices each have entirely disjoint vertex sets for themselves, then that would probably ensure that they're very likely quasi-normal, quasi-orthogonal.
I think I've thought about both of these ideas. At least for one of them, when I was giving my call on this, and I applied it to Freebase for like link prediction. I think there are like really a lot of natural extensions. Like for example, like having the inner product, the dot product between two different vertex codes actually means something. Probably the most natural thing would be having their dot product represent their correlation, in some sense. I think for the second, it's also a very like, I've thought about this too, where let's assume that like we have a set of K, or like let's say we have a set of M graphs, and the dimensionality of these graphs is much larger than the number of these graphs. So maybe first there could be an intermediate step where I have, where I assign each graph to a lower dimensional vector, and really like the dimension of of this embedding really needs to be probably linear with M, or sublinear with M, something like that. And then I can build graphs using the compressions, these m-dimensional compressions of these graphs, or these m-dimensional codes. And then to decompress, I can just, take the transpose of this matrix. So I've also thought about like, how do I abstract a graph into a vertex itself, and then build graphs of graphs essentially. So yeah, I think there are a lot of like really cool extensions or things you can do along this kind of tensor product linearity line of thought. Yeah.
Okay. Thanks for that.
All right, so let me check if we have any more last minute comments or questions to Frank. Otherwise, I think we had a great discussion today, and you raised a very important topic, Frank. So, I mean, just before we conclude, so I hope you would be willing to share your slides so that I can link them from the website.
Oh yeah, sure. How should I just?
So it's just send a PDF by email to me so that I can link it.
Okay.
Along with the links to your archive publications, both of these materials that you mentioned, and I already can confirm that I received the links from Paul and Dennis, so thank you for that. Okay, but thank you very much, Frank. So despite of disturbances, we made it, I think, and it was a successful event, so thanks a lot, and thank you all for coming. So maybe the very, very last message, I saw people joining like at 1 hour later, so maybe it's still because of the daylight savings time, so that the calendars wasn't updated. So please check next time. So the next time we meet, so because of Thanksgiving, so we are meeting in 3 weeks from now, so already in December. So I see you all there. So have a great Thanksgiving week and day in the States. And goodbye for now.
All right. Thank you so much, everybody.
Yes. Thank you.
Bye-bye. Thanks, Frank. Thanks, Evgeny.
Yeah. Thanks, Paul. I mean, yes, thank you.